Good morning. Like I said at the beginning of last class, we'd start with this question as a review, and I thought we would do a little Zoom poll too. Uh, Power sets. We have E, a set containing a 0 and 1. And there's two questions from this. How many elements are there in the power set, and what does the power set look like in list notation? So if you want, you can try it yourself, or you can do this fancy little Zoom poll and answer it there. Why not? So you can take some time to do it yourself, or you can just answer it on the poll, either or, and we'll go through the answers in, like, say, a minute or two. If you have any questions from previous lecture, you can put them in chat or ask them. I'm happy to do that at the same time. What a nice abrupt way to start a lecture, right? I'll answer that question after the practice exercise. Okay, so 13 people have put in their responses, 14 now. The element question is going fairly okay. The list notation question is struggling a little bit. But this is good. This is good. It's, first thing in the lecture, so we have time to talk about this. Okay, so I'll leave the poll open because why not? If you're still working on it, great. Um, but let's talk about cardinality again. So if we take our original set, we know that in that set, E, there are a total of two elements. So to figure out how many elements are going to be in the power set, we just take 2 and raise it to that power. So 2 to the number of elements in E. So if E has two elements in it, we know that's 2 to the 2, which is just 2 times itself twice. So we know there will be 4 elements in it in total. And the second question in the poll, all of those things have 4 things in them. So the second question should kind of tell you after you answered the first how many elements will be in that power set. So that's a little trick that'll tell you how many things there are. And when we did that little tree structure last week, that would give you an idea of roughly why that happens. Because basically, for every element in that original set, you ask, do I want to include it? Yes or no. So basically, the 0, there's like two options if you want to include it or not. The 1, there's two options, include it or not. So it's like 2 times 2, there's 4 total different options. And this idea of yes, no, isn't just like a one and done thing in the course. We'll see it again with logic and creating, like, how many different ways can things be true and false. It's a common logical thing that happens. So uh, like, do pay attention to how that sort of logic works with uh, we have an option here. Do we want to include this or not? Second thing, yes or no. Third thing, yes or no. So with list notation, we can start with an empty set and we can say, okay, do we want to add 0? And if we don't add 0, if we say no, we're still left with the empty set. But if we add 0, we get a set with 0 in it. Okay. And then we can do the same thing for our second element. We can ask ourselves, do we want to add 1? Okay, that's right above my head. Let me just make me a little bit smaller just in case that gets to be problematic. And at each step, we can say either no or yes. If we have our empty set and we don't add 1, then we're left with the empty set. If we do add 1, we get the set containing 1. When we go to our set containing 0, if we don't add 1, we're just left with a set containing 0. And if we do add 1, we're left with a set containing, 0 and 1. So in the end, these are all the different possible subsets that we have. Now, when we form the power set of E, our final step is to take all of these individual elements, so the empty set, the set containing 1, the set containing 0, and the set containing 0 and 1, and we put these all into their own set. So our final result is the set containing the empty set, the set containing 1, the set containing 0, and the set containing 0 and 1. So, I mean, the order here doesn't matter. In the little poll, these were reversed, but it's the same outcome. So yeah, there's a lot of brackets here because all of the elements here happen to be sets. So it does look a little bit ugly. It is a little notation heavy. So I believe in the poll, this was the third response. But in the power set, all of the elements are just other sets. So yeah, it's ugly. That's okay. So there are 4 elements, and these are the 4 elements. You have the empty set, you have the set containing 1, you have the set containing 0, and you have the set containing 0 and 1. These are kind of like the pictures. You have a picture with nothing in it, you have a picture with just the first person, you have a picture with the other person, and then you have a picture with both people. So these are sort of why I use pictures, because you can think of pictures as like sets in a way. It's not just a person, it's a person inside of something. In the poll, was one of the answers without brackets? Yes, one of the answers was without brackets. In fact, 2 of the answers were without brackets. If I drag it onto the screen, it doesn't actually show, but essentially, I can't even copy and paste. Share results. I think you can see the poll results now. So the third response for number 2 was the correct response. And if you look at number 1, none of those had brackets for the elements. So the empty set is fine, and the last one is fine, but those have to be within a set. And 0 and 1 also need to be within a set because 0 and 1 are not just supposed to be elements on their own. They're supposed to be the set containing 0, the set containing 1. The second one, again, those all need to be within a set. And the third one, again, we need more than just 0 or 1 on its own. 0, it has to be the set containing 0 and the set containing 1, because all of those elements are supposed to be sets. So the brackets really are important here. So we have to keep the definition of the power set in mind. The power set is about all the different possible subsets. That's the whole point. So there was a crazy question at the beginning, and I say crazy because there's just a lot of brackets involved, and it might be worth doing. Uh, what is the power set of this beast, of that thing? So basically, this is the element. So it's a set containing 1 element. Uh, it's a set containing the element, the set containing the set containing A. So we know there's 1 element here, which means there's going to be two elements in the power set. So what this is going to look like is it's going to be the empty set is going to be one of the elements because whatever subset we can make, we can always have a subset with no elements. And the last possible element is going to be uh, the case where we just have the set itself as an element. So that is what the power set for that could look like. And if we do a tree, I mean, it would look very similar. We could ask ourselves, do we want to add the set containing A? If we say no, we're left with this. If we say yes, we get that thing right there. So when we put that inside, we end up with these two elements. So as you can see, it can get kind of ugly, but if we go through the process, it ends up being exactly the same, no matter how ugly the original sets are. You just have to keep in mind they're just symbols, so if we just treat them as symbols just like A and B, it'll turn out the same. We just have to keep track of all the ugliness. So are there any questions about power sets before we move forward? Okay. Okay, so the next section that we have is on set operations. Well, a power set is one of the set operations, but with a power set, it's just on one. Most of these set operations are on multiple, and these set operations are usually a lot easier to deal with because you can visualize these a lot more easily. So usually with these things, I like to do the more challenging ones first because this is at the beginning of a section, we can usually use our the most of our mental energy. And then as we go on, we start to get a little bit more tired. So we put the easier ones at the end. So the first set operation that we have is called the complement. So when we have a set, uh, we should establish something first. Usually we have what is known as a universe. And this is basically all of the objects that we entertain. So a set is placed within a universe. So, for instance, if I talk about all of the Ling 324 students, usually my universe would then be all of the people in the world or all of the people at SFU. I'm making an underlying assumption that I'm talking about people. Uh, in a course like this, when we have a universe, if it's relevant, I usually define the universe so that way you know what you're looking at. Like if it's consonants or vowels, you usually assume the universe is letters, but I specify that if it's important. So if you have a set A, we define the complement of A as everything that's not in A. So if we have A here, as in this white circle, then a complement is everything outside of that circle. And you don't ever need to draw these out. You just need to know the symbols and what the elements are. So if you know what the elements in A are and you know what the universe is, you need to be able to know what the elements in A complement are. All of these pictures are just to help you visualize things if you need them. So, as an example, let's assume that A in this case is all the vowels. So A, E, I, O, and U are in A here. and the universe are all of the English letters. Then what is an A complement? Well, a complement is going to be all of the English consonants. So in a complement, we would get B, C, D, F, G, H, J, K, L, M, N, P, U, R, S, T, V, W, X, Y, and Z. So this is a nice visual representation of what is an A and what is an A complement. So yeah, this is the same term complement that we use in syntax, but the meaning is very different in terms of the operators. And if you've taken other math courses or statistics courses, we use A with a bar, with a little uh, complement symbol here, but you might see this written as A with a C above or A with a little bar on top. These all mean the same thing. You might just see them in different, written differently. So if you look online and look for resources, you may see one of these three. They all mean the same thing. The last thing I want to focus on here is this little definition. So even though I talk about these visually and talk about them a little bit more casually, it's also important to be able to read these definitions. So just to sort of walk through this with you, this says that the complement of A is defined as being all of the X in the universe. So this just says all of the things in the universe. And again, this bar is read as such that. So this is all of the things in our universe such that X is not in A. So all of the elements in the universe that X is not part of the set that we're looking at A. So that basically just refers to the shaded part outside of A. So is the complement okay for people? Thumbs up. That's good. We're not going to do practice for each individual operator. We'll just do practice for all of them at the very end. Oh, one more term. This is called a unary operator. Unary from unit meaning one, because you only need one set for this to work on. So if you have just A, you can get A complement. Okay, the second one is called an intersection. The intersection is the first of what are called our binary operators. Binary, bi meaning two, because you need two sets for these to operate on. And the intersection means that if you have two sets A and B, these are the elements that are common or in both of those two sets. So these are the things that are in both A and B. So our definition here, I'll run through the definition first. If we have A intersection B, these are the sets of things X, so sets of items X, where X is in A and X is in B. So this refers specifically to this area. And we use an upside down U here, this symbol. If the symbols are a little bit confusing, uh, how I initially thought about this is I used to think about this as like a cup that like went on top of something that sort of trapped things. So it traps sort of the similar objects between the two. I don't know if that visualization helps people, but that's how I originally thought about it. So let's do a little example here. Let's say that A has A, C, E, and G in it. So that's our set A. And B has our vowels in it, A, E, I, O, and U. So we can write out A, C, E, G, and A, E, I, O, U in different sets. And what we'll do at this point is we'll take the common ones and we'll put them in the middle. So A and E are common, and what I'll do is I'll just get rid of them in each of those sets, just so they're not repeated. And what we're saying here is because A and E are common to both sets, then A and E are in the intersection. So formally I have it written down here, but I'll write it out again. The intersection of A and B consists of the elements little a and little e, because those are common to both sets. That's just what the intersection says. Now, in natural language, you might think, well, what's the point of an intersection in natural language? What words in English would we use this for? Well, think about uh, let's say you have a set of kids and you have a set of happy people, and you want to say, I want to find all of the happy kids out there. Well, in order to find the set of happy kids, you have to find the set of things that are happy and the set of things that are kids, and you would find the intersection of those things. And whatever's happy and whatever's a kid, you'd find the things that are both, and then you have the set of happy kids. So basically, when you want to find something that's both an adjective and a noun, you have to be careful here because this doesn't work with all adjectives, just a certain type, and we'll explore that a little bit later in the course. Uh, these specific noun phrases modified by adjectives are like a type of adjective that works with an intersection operator. So these are relevant in natural language too, and can be used to describe these types of nouns that are modified by certain adjectives. So these operators are used in natural language too. So this is the intersection. The next one is the okay, but before one last thing, one last thing. Think about the word "and" with this. That's my last one. If you want your little cheat sheet in your head, think about the word "and" for the intersection. "And" is your best friend. Because this contrasts with the next operator, which is the union, which you can think of with the word "or." Or. So the union is another binary operator, which takes all of the elements that are in either A or B or both. So basically, if we use the same sets as before, which was A, C, E, G, and A, E, I, O, U, again, we're going to put the common elements A and E in the center and just spread these out a little bit. Basically, with the union, we're just taking all of them. So if we write this out, again, I have it down here, but I will write it again. A union B is C, G, A, E, I, O, and U. Again, the order doesn't matter because it's a set, but it's just basically all the elements in both sets. And remember, you can just write out everything in A and everything in B, and that's fine because if you repeat elements, it doesn't really matter. But this is the union. And this is just a U. So you can remember U for union or an upside down cup. I've seen things on the internet where it's like you take both sets and you just pour them into the cup. That's one way of remembering it visually. But the key word here is or. And in natural language, this works the same way. It's like, uh, I don't know, like if you're looking for things, or you can say, uh, bring punch or pie. As long as you bring one of the two, you're happy. Or you could bring both. That's another thing. The or doesn't mean that you have to bring just one or the other. You could bring both. Like you're happy with either. So the word or works very well. So yes, that's the union. Don't know if I have anything more to say about this operator, but we do have one more here, and this last one isn't used that often in linguistics, but it is worth mentioning, which is the difference. So the difference operator is basically subtracting one set from the other. So you can call it a difference, or I just call it A minus B, because if you say A minus B, everyone understands what you're talking about, and it's a little bit easier than understanding when you say the difference of B and A or the difference of A and B. Not everybody understands what that means straight away, so A minus B works just fine, and it's what you would expect it to mean. So uh, I'm using the same sets for A and B every single time here. So C, G, A, E, I, O, U, just writing them down without removing similarities first. So what's happening with A minus B is I'm taking everything in A and I'm removing everything from B. So this means the things that are just in B are being taken out, and the things that are common to A and B are being removed as well. So if I take A minus B, what I'm left with in this case is just C and G. So visually, you can see this very clearly, but if you just do this with the sets themselves, it might not be so easy to do. So there's a nice way of doing this without the picture. So how I recommend doing this is to just write out the first set that you're taking. If you're doing A minus B, just write out A and just go through B. And whenever you see something in B that is in A, just like literally scribble it out. So when you go through B and you see A, you say, okay, A is in B, so scribble that out. Then you go through E, okay, E is in B, scribble that out. I is in B, I don't see I don't see O, I don't see U. Okay, I'm just left with C and G, we're done. And I say that because sometimes with things like A minus B, what I see is people start removing things that aren't there, or there's nothing to be removed, and people get confused. So that's just a little method of doing it when you can't draw a picture, or if you're pressed for time and can't draw a picture for whatever reason. So the definition here, again, this is the set of things, X, such that that element is in A, but the element is not in B. So that corresponds to this little shaded area here. So in natural language, I mean, the definition corresponds to really what's in top on the top. Like for instance, I want the dogs that are not happy. This is really like saying I want the set of dogs minus the set of things that are happy. Now, we can always rephrase this. You could say dogs intersection happy complement. So that's another way of thinking about things. And we'll see a little law later that we can use to convert these sets. So we don't actually need a difference operator. We can always think about it in different terms, but a difference operator for our brains is a little bit simpler than thinking about things in terms of intersections and complements. So we'll get to that in a little bit. But for now, we can just use a difference operator. So I do have practice questions on the next slide, but are there any questions about the operators before we tackle those practice questions? If there were more elements in A that were not in B, they aren't included in the final answer, right? I'm not quite sure well, okay, so let's say that Z and X were in there. Then A minus B would also include Z and X because B doesn't have Z and X to remove. So A minus B would still be CGZX in this case. A minus b only removes it. So a minus b is basically all of a, but it just removes the things from b. So um, it only takes away a, e, I, o, u. It takes away a, it takes away e, but there's no I, o, u to take away. If a had I, then it would take away I. If a had o, it would take away o. If a had u, it would take away u. But a doesn't have I, o, u, so it doesn't take away those. Like here's something. Imagine if I had a minus the empty set. Like what would we get if we did a minus the empty set? Like we would just get a back. If we took a minus the empty set, we're doing a and we're taking away nothing. We just get a back. So like that's something we can do with the set difference. It's one of those like useless operators. Well, not useless, but yeah, I mean it would be useless in that case. A take away nothing. It's kind of like, you know, 6 minus 0, that sort of thing. I do say minus in this sense because it is very similar to minus when we think about the empty set in 0. Okay, so uh oh no, that was a practice question. Oh, whatever. So let's take a few minutes, 4 minutes or so to try to run through these. So try some of these on your own and I'll go through the answers in 4 minutes. Again, if you have any questions when you go through these, bug me in chat or over voice and I'll answer them when I can. The sets are pretty small, so they shouldn't take too long, but if you are struggling, remember, just draw pictures. If you have to visualize them, visualize them. There's no shame in visualizing. Use as many visual tricks as you can before you get good at the notation on its own. Okay, I believe I have drawn this picture correctly. It's a lot of circles here. So B is shared by K and M. C is just an L. D is shared by L and M, and A is just in K. Okay, so here's a nice visual representation of what's going on with three sets. Again, it is a little bit ugly, and when you have four sets or more, the pictures are very difficult to draw. So it is good to be able to do this without images, but when we first start to practice, the more visualization we get, uh, the better it is for illustrative purposes. So if you do have answers to these, feel free to type in chat the best that you can. The more practice you actually commit to, the better you do in the end, especially if this is the first time you're doing it. So the first one was K union L. Which elements are in K union L? So these are the things that are in either K or L or both of these. So this would be the area that is right here. So things that are, yeah, A, B, C, or D. So you could do that image. You could basically just draw the little lines over everything in K and everything in L, or what you could do above is just write out everything in K and write out everything in L, and you would get your set. I need to write out the set first, and then I need to draw the lines, otherwise it's going to be difficult to erase. Next, K union M, we could do the same thing, everything in K or everything in M. ABD, yeah, so what we could do here is we could do the same thing. We could write out everything in K, which is A and B, and then we could write out everything in M, which is B and D. And because we have two repeated elements, what we could do is we could just remove one because repeated elements don't count, and we would get ABD. So fantastic. Or we could just write ABD based on, the shared bit of info here, or we could find B repeated and remove one in our head. Lots of different strategies here. Okay, L union the empty set. What about this one? C and D. Yeah. So when we have L union the empty set, basically this just means that we're taking L on its own and we're taking L with nothing because the empty set has nothing in it. So it's everything in L with nothing else. So we're just left with L.
So just 1 second. It wouldn't be C, D, and empty set. It would just be C, D.
Yeah. So basically, this is the same thing as saying, I want everything in CD union empty set, which has nothing in it. So, like, again, I just want to remind you that when we write the empty set, this is like taking two brackets on the outside with nothing in it. So when we take a look at those elements inside, there are no elements. So this is another way of thinking about it. So when we go through the process of taking all of the shared elements, or not all the shared elements, but all the elements in either, there's no elements here to take from that empty set. So it would be incorrect to write null C and D, because if you write null C and D, then what you're saying is that this is another element, but you don't have this set. Like the empty set, basically what you'd be saying then is that the empty set would look something like that, but that's not what you have. Sorry, that's going into my face. Those are different things. The empty set with these set operations is basically just zero. It's nothing. Okay, fourth one, K intersection L. So these are the things that are shared by both K and L. This is just the empty set. So there's nothing in common here. So this is the empty set. So this can be written as that. And the empty set is just a symbol for that set with no shared elements. Correct, Bradley. It is not the set containing the empty set. It's just the set with nothing inside, which is just the empty set symbol on its own. So yeah, if this symbol is confusing you a little bit, it is okay to work under this visualization of it. Um, it just is a little bit messier, so you will have to get used to that. But conceptually, that might work a little bit better at first. Um, but you will have to get used to the symbol, the little circle with the line through it. Okay, K intersection K. What's this one going to be? So any set intersected with itself is just going to be that same set K. So it's just going to be A and B. So yeah, basically you're taking this set and you're intersecting it with itself, which is just going to be that same set. Okay, the next two ones, we're taking a set together with another pair of sets. So the key here is that we do the sets inside the brackets first. So it's just sort of like math. We do the brackets first, and then we do the outside. So first we do L intersection M. So first we're looking at this bit. So we would get K intersection just D, and we're asking what does K have in common with just D? And the answer is nothing. There is nothing in common with just K and D. Is putting the null symbol in place of the empty brackets incorrect, or are they interchangeable? They're interchangeable. They're definitionally equivalent. So yeah, K intersection L intersection M is the empty set. Let's take a look at K intersection L union M. These bars. B, E, okay. I have to actually do this. L union M. Did we do this one yet? We didn't do L union M. So L union M, we're basically doing K intersection B, C, D, because L union M is everything down here. And we're taking a look at what K has in common with B, C, D. Well, K is A and B, and the only thing that A and B has in common with B, C, and D is just B. So yes, K intersection L, U, and M is just B. And Bradley has gone ahead and done K minus M. So yeah, we take K, which is A and B, and we're subtracting M, which is B and D. So basically we're taking A and B and we're subtracting B from it because we see B in here, and we're left with A. So visually what we're doing here is we're basically taking K and we're saying, I want to get rid of everything in here. And then we're left with A. So that would be K minus M. So in this case, we're just left with this area. That's a visual representation of what K minus M would be. Okay, what about M minus L? M minus L. Yeah, this one would be B. So we're basically taking just this area here. So we're removing everything in this area from M. And finally, K minus the empty set. K minus the empty set, we're basically taking K and we're removing literally nothing. So K minus M just gives us K, which in this case is just AB. Okay. Are there any questions about those set operation exercises? I enjoy that better than inferences. Yeah. Inferences are usually one of the least enjoyed parts of the course, from my experience. Um, which is why we do it first. It's also why it's worth the least amount compared to anything else in the course. I make it very small relative to everything else. So we'll do set laws and everything on Tuesday next week. Um, I'm going to talk a little bit about assignment 2 right now. And I think we can finish most of the things on Tuesday. We might push a little bit back to next Friday, but the whole course is set up so that way um, we have a little bit of time without having to push back the first test or whatever. I do want to give you a little hint about assignment 2 and just sort of talk about it before today's class. So at this point, you can do question 1 just fine on assignment 2, and you can do most of 2. You cannot do 2D or 2F right now. Can you help us to facilitate getting into groups for the assignment? Um, hmm,
You can always use the discussion thing on the canvas.
Yeah, I just found that it was like I never really knew when those discussions got posted, so I didn't know if they had already had groups or not.
yeah, either I can start one or you can start one. Not many people are actually in groups in the first one. How many people are in the LSU Discord for this course? I don't know myself. There's a few people. Um, because I know that people who are in this lecture, in this room right now, are probably more likely to want to be in a group than people who aren't. And a lot of the people in this chat room right now have been submitting alone. How many people in this class, in this room right now, want to be in a group who are not? Okay, so if you are not in a group who want to be in a group, um, you should, if you can, there's a Discord link there. I suggest joining that and talking. That might be the best way because that way you don't have to make a discussion group right now and you can just join right at the moment. Maybe the fastest way. Uh, yeah, that way we don't have to. This isn't me trying to not do it. This is just me saying we have an instant solution, so let's just work with that solution now. But if this comes up again and other people want to do it for assignment 3, we'll definitely do the discussion board again. Okay, so question 1 and 2 you can all definitely do right now. 3, 4, and 5 we'll be able to do next week. Understanding extension. So, like I said, once we do an assignment and we talk about it and we go through solutions, we do something that's a little bit more involved and in depth based on that material. Something that's a little bit more thinky and not as um, similar to the stuff we do in lecture, but still uses the material that we've done. So for inferences, we're going to do a question on entailment that involves hierarchies. So there's one that's about verbs and adverbs, and there's one that's about animal hierarchies. So there's things called downward entailment and upward entailment, depending on a specific and general categories. So you can read a little bit about this one. I don't have many tips about it. I think this one is fairly explanatory, self-explanatory. But if you have questions, email me. Like I will give tips. I'll help you with these questions. Like don't feel you're on your own. ask if you have questions. Don't like cry about these if for some reason you struggle a lot. I want to give a tip about this last one, which is about a chord exchange. You have to read this very, very brief conversation about a chord exchange and use semantic inferences to determine whether or not the court made the correct assumption. There's a specific line. Focus on this line for your inferences. This is the tip I'll give you, because I realize that it might not be obvious which line you have to analyze, and it might seem like you have to analyze a lot in this conversation. This is the specific 2 lines to analyze in this conversation. So focus on this one. There's one inference, that's it. So that's what I have to say for this second question for the understanding and extension. Again, if you have any questions about these, like, please ask. Please ask. You're not alone. It's not just you and your group members. You can talk to me too. It's okay. So that's it for today. If you have any other questions, you can stick around or email discussion board, all that stuff. Enjoy the rest of your week.
I have 2 questions.
Yep.
What is upward entailing and downward entailing mean?
So I've explained that in the question, but just to go over it, we have usually in a chart or in a tree like this, we have general things on top and we have specific things on the bottom. If the general entails the specific, we call this downward entailment. So something more general entails the specific. And if something more specific entails something more general, we call this upward entailment. So it's basically your job to say that something specific entails something more general, or something general entails something more specific. So you'll have to figure that out by coming up with an example sentence or 2. The lecture recording will be posted within a few hours.
Also, are we ready to do the second practice exercise?
The second practice exercise, let me check. I think you're ready to do it because there's no questions about set laws on the second practice exercise. So yes, you are okay to do the second one now.
Okay, thank you.
There is one question about the IPA on there, but it gave you a chart and I tried to make it very simple. So that way you can do something with set notation with the IPA so you can see how it applies to phonetics. So don't let that scare you, but it's just one application of what we've seen to something that is not syntax.